Okay, well, good morning, afternoon, everybody. It's my pleasure to introduce today's speaker, Fady Bishara, who's a physicist at the DESI in Hamburg, and he's going to tell us about dark matter, direct detection, and effective field theories. The floor is yours, Fady. Thank you.
Thanks, Venus. Okay, so yeah, I will talk about, dark matter direct detection and effective field theories is a huge topic. So I just thought aspects would be just some ideas. I'll start slow with direct detection and then we'll go from an example and then I'll show some more examples. But the very first part, I'll try to be very start from the basics. So if something is not clear in the beginning, please stop me. That's important that we're on the same page. So yeah, so dark matter is there is a huge amount of evidence. There's unequivocal experimental evidence that there is dark matter. We see this in galactic rotation curves. That's the top left panel. We see it in the CMB power spectrum, top right panel. We see it in weak lensing, bottom left. This is the bullet cluster. And we see it in strong lensing. So there's an amount of material that is between us and between these galaxies that is lensing the light that's coming through, and it's not luminous. So there's just no question that there's this so-called missing mass problem. The thing is that this evidence is really only from gravitational interactions. I mean, we don't have any evidence whatsoever that dark matter is a particle in nature. There could be in the future if one can measure self-interaction of dark matter that is stronger than its gravitational self-interactions, then it would be a clear signal. But so far, there's nothing. However, it's not unreasonable to posit that it's particle in nature. Everything that we know that the universe is made out of is made out of particles. And the missing mass is not unreasonable to say that it's also a particle. I think it's not simply that we're particle physicists and everything should be a particle. I think it really is a reasonable thing to posit. And if it is a particle, then we can detect it in many different ways. And there's been a big program for the last 25, 40 years, 20, 40 years of trying to look for it somehow. And one option is to just set up a laboratory and wait. We're flying through a dark matter halo. We're flying through a dark matter wind. Wait for this dark matter to interact with our detector and look for that signal. Another one is the dark matter is again in the halo. It's moving around a little bit, and it can decay with long enough lifetime. So that's another thing that one can look for, and it has been looked for and put a very strong bound on the lifetime of dark matter. But it can also annihilate with each other into standard model particles. And the last typical search is to look for it in colliders, so the other way around. So time goes from left to right here, so if you want. So standard model goes to dark matter on the right-hand side here. And the thing that, I mean, you probably have seen this 1,000 times if you've seen dark matter talks, but the thing that I'd like to point out is that these different search strategies come with different very different characteristic energy scales. So 200 MeV, 100 GeV, or whatever the dark matter mass is, essentially sets this scale, and then the center of mass of the collider, which is around a TeV. So since the focus of this,
can you comment on why do they come with such different scales? Just
yeah, it's just the characteristic. So the reason why this one is very low, 200 MeV, is, let's say the standard model is something like 100 GeV nucleus that you're interacting with. And the dark matter has a velocity of 10 to the minus 3. So just elastic scattering of dark matter on this nucleus, it gives you a maximum characteristic scale of about 200 MeV. So the scale here is set by the fact that the masses of the dark matter and the standard model target that you're scattering with, and the velocity of dark matter, which is very, very small. On the other hand, in indirect detection, the relative velocity of dark matter is very small, so it's not really adding anything to this process. But what's setting the interaction scale is the mass of the dark matter, because you have essentially the energy coming in is 2 times the mass of the dark matter, and then that goes into standard model. And then the last one is because you are, I mean, this is much more, you know, sort of with a wiggle here, because it depends on what you're producing actually, if you're actually producing dark matter or not. So, but root S hat at the LHC roughly for 13 TeV, you probably have most of the collision happening around a TeV scale or so. So that's, does this?
Okay, no, I see what you're saying.
So yeah, and in fact, the fact that these different dark matter direct detection has so many scales and so many parameters that decide what's important and what's not important, and that's what makes this actually a very difficult problem to tackle without effective field theory, and it's indeed why effective field theory is the right tool here. So so since I'm going to be mostly focusing on direct detection, so let's look at a direct detection experiment. So this is the Xenon, now it's called 1 ton, and in the future it will be 20 ton. They're expanding the volume. The 1 ton refers to the fiducial volume, or actually I think it refers to the total volume of the detector. This is a 2-phase detector. So the bottom here, the bottom cylinder is made out of liquid xenon. This is LXE here, liquid xenon. And the top sort of cylinder cap here is made out of gaseous xenon. And on the top and on the bottom of the detector, there are photomultiplier tube arrays. That's these little circles that you see at the top and at the bottom. So what do they look for? So they look for a particle, so something that comes in, interacts in the detector. When it interacts with the xenon, elastically with the xenon atom, it excites the atom, the nucleus, which emits when it de-excites, it emits a photon very quickly, and that's the signal right here. So as soon as this thing interacts, if it's heavy enough to excite the xenon, and that's important actually, if it's heavy enough to excite the xenon atom to make this 200 MeV momentum exchange, then it will emit a photon, and then you see this photon right away, and you see it at the top and at the bottom. As you can see, there's a hit here and there's a hit at the top. Now, during this interaction, so there's also some free electrons that get excited, sort of freed or ionized, if you want. And these electrons drift in this electromagnetic field, this electric field, sorry, on the right, and they drift much slower, obviously, than the speed of light. So they take a little bit of a time delay, and they drift, and then once they get into the gaseous, they again excite. Okay, I don't exactly know, to be honest, exactly what happens in this part, but they either recombine or excite something and emit another photon or another bunch of photons, because there's probably more than one electron, so there's a bigger signal here, and these bunch of photons. So it took time for these things to drift. Then they make a signal here, and then they make less, somewhat less of a signal here, because probably there's a bunch of photons, and they're closer to the top detector, so they're more localized, and at the bottom they get more spread out. And the fact that you have these two signals allows you to, so the first signal allows you to sort of localize more or less this. It's essentially it's not very many photons in the first signal, so it's much more localized. A few photons, it's much more localized in, if you want, the XY space, which is in the disk. And then the drift time allows you to say how deep this thing is in the detector. And the fact that, and what this allows you to do is allows you to make sure that this interaction came from the center of the detector, from the fiducial volume, which is shielded from external radiation and other things, muons and all that, whatever, neutrons and decays and things like this that can happen outside. So this allows them to be to reject a lot of the background. And I mentioned in passing that this first signal requires the particle to be heavy, because in order to transfer enough momentum to the heavy nucleus, which is 100 GeV, in xenon it's 131, you need to be heavy enough. So if you have things like scattering on electrons, which, if you've heard, there was an sort of low mass excess at xenon. This was just based on this S2 signal because S1 was not possible to produce. It was some light dark matter in the GeV range, and it produced some excess of events where they didn't expect any. So the status of this is unknown at the moment. What's causing it, as far as I know.
Sorry, question, Fady.
Yes, please.
So do you know why they use xenon?
That's a good question. Why did I use xenon? Well, it needs to be. Well, they use noble gases, so they use xenon and argon, and the reason for this is
because the xenon nucleus would be quite heavy, so a lighter.
It's heavy. Yeah.
Presumably, you want to avoid chemical reactions.
It needs to be inert, that's for sure.
Sure. It needs to be noble gas, but yeah, a lighter noble gas with a lighter nucleus would allow you, I don't know, lighter dark matter.
But there are lighter materials. Sorry, I didn't mean to suggest that all of them are heavy. So there is actually experiments so there was an experiment called Pico, and this experiment looked for so essentially what happens is that the dark matter enters and it scatters, and the volume is near critical, so it's you superheat the volume and it makes bubbles essentially. And that experiment had fluorine and iodine in it. So these are lighter nuclei, around mass number 19 or so is the fluorine. So, but again, fluorine. No, I mean, you need something inert. Indeed, you cannot have something that's interacting. You cannot have something that's that has too much that has short lifetimes. That doesn't work, obviously. Things like this.
Yeah, no, of course. I mean, I know it has to be a noble gas. Just didn't know why they go with such a.
No, that's a good question. I still didn't super precisely answer your question. I'm sorry, but
no, it's good. And then so they can tell the difference between the S2 and the S1 signal, right?
Yes, I mean the pulse shape is very different and the timing is very different. So if you see one, it's usually very small signal because you have few photons that are released, and then the big one is when all the electrons finally make it to the gaseous phase, and then it makes a lot of photons. Then. So the shape of the signal is different, indeed. Yeah.
So I mean, if the density of dark matter was high, so it would be a lighter candidate, and it hit you near the top photon multipliers, they would be able to tell the difference that it is.
If it's, I mean, the gas is not dense enough probably for the dark matter to actually. It's much more likely that it hits in. That it scatters in the. I mean, it's possible, of course.
Yeah.
With a smaller probability. Absolutely.
I was just thinking, I mean, with two different dark matter candidates, could the S1 of one be very similar to S2 of another? And
indeed. So in effect, if you have very light dark matter that scatters on electrons directly, that's the signal at 1 GeV. So if you have 1 GeV dark matter, it's not likely to leave an S1 signal and only leaves an S2 signal. And indeed, so different dark matter candidates, and actually you can see here, this curve up here, this xenon 1-ton 2019, is electron scatters. And you see it's covering, so this x-axis here, this is from the PDG review. It's a very nice review on dark matter. And they have a sort of the combined plot of the current direct detection bounds. And xenon 1-ton 20. So I showed you xenon because it's the strongest bound at the moment. So what is this bounding? It's bounding the interaction cross-section between the dark matter candidate and the standard model, essentially, and the nucleus. So lower means smaller cross-sections, means weaker interactions. And you see, so this part of the curve 2018 is this S1, S2 story, and this xenon 1-ton 2019 here is just the S2 story, where it's a light dark matter candidate below 10 GeV, down to, well, not quite 1 GeV, but close to it, I guess. So it's lighter range, and there are other experiments that are trying to probe the light range of dark matter. But you see, this range is for, this was all motivated. I mean, not purely, but supersymmetry was sort of a driver for this WIMP, and then having these targets around 100 GeV is really putting a very strong bound on these sort of mass ranges of dark matter.
Yeah.
And you see that, just from 2017, super CDMS was sort of the strongest bound. I think there's many missing ones. There's like Xenon 10 and all that stuff that's not here on this plot to make it readable, but the bounds got stronger by a few orders of magnitude in just a few years, and these bounds keep going down. Now, at some point, what happens is you hit this shaded blue thing at the bottom, which is the neutrino scattering. So neutrinos also interact like dark matter. So they're light, so that the signals might be a bit different, and for different experiments, maybe it's you can distinguish the difference. One thing that you can distinguish is that is the direction of dark matter should be coming from one direction, whereas neutrinos will probably be coming from all directions. So people are trying to work on directional detection of dark matter, but that's a very hard problem. It's dark matter scatters only once because the cross section is so small. And if it scatters only once, it's very hard to tell where it was coming from.
Can you say, why is there a direction dependence expected in the dark matter?
Yeah, the dark matter. So the dark matter. Sorry?
That somehow surprises me.
Yeah, so the dark matter comes from one direction because so its the velocity is very small in the halo. And so its velocity in the halo, this velocity dispersion is something like 10 to the minus 3 in natural units. But what sets the velocity is the fact that the galaxy, the galaxy is rotating in this halo. So the solar system has a peculiar velocity in this halo, and the Earth also, of course, rotates around the sun, so that adds a bit of a component. But what mainly sets the velocity is the fact that the galaxy is rotating and we're moving. The solar system is moving in one direction in this wind. So that's really what's setting the direction of dark matter.
Okay, so you expect it from it as an ambient medium which we are traveling through, and we are setting the velocity.
Yes, indeed. Okay. The medium is essentially stationary, and we're moving through it with a velocity, indeed. I mean, of course, when you want higher corrections, then you take everything. You take the fact that the velocity, that the dark matter also has a dispersion and all that stuff. But yeah, what sets the main component is our speed.
Sorry, another question, if I may.
Yeah.
So why is the neutrino coherent scattering so constraining in the lower masses?
Yeah, okay, good. So this has to do with different, okay, I'm not going to be able to answer this super precisely, but I can tell you that this plateau here is solar neutrinos.
Oh, thank you.
So these are neutrinos coming from the sun, and I guess these would also be directional. And then there's other a component of the background of the neutrinos that comes to this high tail from another source. But these ones I think are solar ones in this plateau here.
Thank you. Yeah.
Yeah. So in a volume of a detector, what you have is so we're flying through. So there's essentially a wind of dark matter as these arrows here with some sort of a number density and a velocity. So the interaction rate in this detector is, the flux, if you want, is the number density times the velocity, and the probability that you interact inside this volume is the cross section. So the interaction rate is n, which has units of 1 over length cube, which is GeV minus GeV cube, let's say in units of GeV. Relative velocity is dimensionless, and the cross section is 1 over GeV squared. So this quantity here has a units of GeV, which is a rate. So this is, and for maybe this is a fun tidbit for the students. So this is n sigma v, so you can derive it this way. We just derived it. N sigma v is the interaction rate in the detector. But if you want to compute the relic density of dark matter, it's also n sigma v is the interaction rate. But in that case, you compare that with the Hubble parameter, the Hubble expansion, so that in that case, what you're trying to do is you want to see when this rate becomes weak enough that when essentially n is diluted enough that this interaction freezes out. So, and as the universe expands, as you compare to the expansion rate, the universe expands and gets smaller and smaller, and then at some point you stop interacting anymore. This rate becomes small, and then you freeze out. That's the freeze out. N sigma V. And we're interested in the rate. So not just, so we're interested in the rate in the sense that we are interested in how many hits you get in the detector, the event rate. So typically, so what you typically look at is this interaction rate per unit detector, which is, let's say, one nucleus. Then, of course, at the end, when you want to compute the total rate, you have to multiply by exposure time, how long you've been looking at this detector, and the volume of the detector times Avogadro's number to, whatever, how many targets you actually have. So, so I said in the previous slide, it's N sigma V, but here you see these funny brackets, and we'll talk about them in a second. But the dark matter and the number density of dark matter is non-relativistic. So, and for non-relativistic, the energy particle, the energy density rho is just m times the mass times the number density. And so we just replace it here, and you get rho times rho divided by the dark matter mass times this sigma V. Okay, and then one more step. We're not interested in the total number of hits. We're interested in the differential spectrum of these hits with respect to the recoil energy, and this allows us to, first of all, the detector has a sensitivity that depends on the recoil energy. It's not sensitive for all energies, because at some point there's many things involved in determining these signals. So usually there's a window between 3 and 50 keV recoil energy that they're sensitive to, so you need to be differential. And so we just take the derivative, and the only thing that would depend on the recoil energy is the cross-section part. Now, this funny brackets just come from the fact that here you have a velocity distribution inside the halo. So you need to take the expectation value of this quantity, and so d sigma by der times v, you take the expectation value as you usually would for any statistical quantity. You multiply by the PDF, which is the velocity distribution, and you integrate from the minimum velocity that would give you a signal in the detector up to the maximum velocity. Typically, the maximum velocity is not infinite because the dark matter is gravitationally bound in this halo, and there's an escape velocity to this dark matter. So at some speed, it won't be bound in the halo anymore, and it will just evaporate if you want. So V min up to some V max, and that's it. That's the formula for direct detection rate. If you're trying to do a freeze-out approximation, it's not the velocity distribution in the halo that you're looking for, but it's a thermal average, because now you're not at a zero temperature if you want, and so thermal fluctuations have to be averaged over, and that's what you would do in that case. So dark matter interacts with, I already mentioned, essentially interacting with the nucleus. Okay, so the dark matter comes in, it exchanges momentum with the nucleus, and of course you need a mediator between the dark matter and the nucleus. This is implicit in what I've been saying. If the dark matter is completely secluded, it means that it only has. Let me back up 1 second. That's another possibility, of course, is you have a secluded dark sector that is particle in nature, but doesn't interact with the standard model at all. There's no mediation between this sector and the dark matter. And that would also, that for all intents and purposes is just a gravitationally interacting system. Although it would be interesting to know, and people are thinking about this, if you have such a secluded system, could you still tell that there is some structure of this secluded system by some non-traditional, if you want, gravitational signatures? I don't know, gravitational waves or something else. But inside the nucleus, there are nucleons, and really what the dark matter is doing is it's really interacting with a nucleon. And you see where this is going. Of course, the nucleons have quarks, and really what the dark matter is doing is it's interacting with the quarks inside the nucleons. So, so what we want to do is we want to write down, so this is my, my one slide that I don't expect you to read or fully absorb. It just gives you a picture of what's going on. Okay, I have a whole bunch of scales here, starting from the very lowest scale. At this scale, you have essentially dark matter interacting with nucleons, And these nucleons have a form factor inside of a nucleus. So, my starting point as a particle physicist, input to the nuclear physicist, is interaction of the dark matter with the nucleons. And this is the so-called non-relativistic effective field theory, where the nuclear theorists use to compute the response functions, the form factors inside the nucleus. This NR-EFT is typically what people write is not a Lorentz invariant, but a Galilean invariant theory. And some details that are not super important here, but I will show you some of these interactions because they'll be give you an interesting insight on what's going on. So Qmax here is 200 MeV. If you go up to 1 GeV, then you see that, so between 1 GeV, below 1 GeV, the degrees of freedom that you have are nucleons, pions, hadrons, etc. Hadrons, essentially. You don't have quarks and gluons. An important step is when you go above 1 GeV, then the description now is not in terms of hadrons, but it's in terms of quarks and gluons. So it's the three flavor standard model, because above 1 GeV, the charm and the bottom quarks are too heavy, and the top of obviously and everything else are too heavy. So in the spirit of an EFT, those are degrees of freedom that are not relevant. You cannot excite them. And the only relevant degrees of freedom are the light quarks, the up, down, and strange quarks, plus all the leptons, and etc. When you go up one more step, then you see the charm threshold. Then you go up, you see the bottom threshold. Then the bottom and the charm become active, and all the way up to the electroweak scale, MZ here, we have a standard model, 5-flavor standard model, plus QCD, of course, plus a dark matter candidate. One more step. So below MZ here, I've the degrees of freedom that are too heavy to be excited are the electroweak gauge bosons, the Higgs boson, and the top quark. So those are out of the theory, and that's why it's 5 flavors instead of 6. Above, now we have 6 flavors, all the standard model degrees of freedom, plus a dark matter candidate, up until you hit the scale lambda. So the assumption here is that there is some scale above which there is a complete model of dark matter, below which I only keep the dark matter with effective interactions, with effective operators, in local interactions, if you will, like Fermi theory interacting with the standard model. There are many effects that happen above here. For example, renormalization group running mixes these operators, and there's relevant effects that come from that above. I will show one example. Then below there's QCD and electroweak running. Most notably, electroweak running, what does it do? You would think that's completely irrelevant, and it is, except if you somehow manage to write down a theory of dark matter that doesn't interact with quarks at all. So if you write down such a theory, then you would think I probably don't have interactions with, or very strong interactions with the nucleus, because I don't talk to QCD at all. But what happens here is you can always close a loop of leptons, attach a photon to it, and attach at the other end of the photon, attach quarks. So now you think you don't have any interactions with the quarks, but all of a sudden you have this loop, and even though it's suppressed and it's 10 to the minus 3 or whatever, it still gives you interaction. So the name of the game with EFT and this whole setup, this whole complicated setup, is one thing only, which is to organize your interactions. You want to know what's important and what's not important. And there are so many parameters in this problem. There are parameters that I didn't put here, but I mentioned one of them, which is the velocity of the dark matter, 10 to the minus 3. That's also another scale, another dimensionless scale in the problem. And the mass number of the nucleus. So the number of nucleon in the nucleus depends on what interaction of dark matter you have. Some interactions, like the vector interaction, counts the number of nucleons. So it will be enhanced because it interacts with all the same with all the nucleons, by a factor of 100 in the amplitude, 100 squared in the cross section. That's 10,000. So I have a scale that's 10,000, a dimensional scale that's 10,000, and a dimensional scale that's 10 to the minus 3, and all kinds of other scales in between. And you see, it's just quite a mess to Another thing to contrast with this coherent, this is called coherent enhancement, when you have some interaction that interacts with all the nucleons in the nucleus at the same equally. Contrast this with the spin interaction. The nucleus has one spin. It's whatever. Let's say spin 1/2. So you interact, when you interact spin-spin interaction, you're interacting with the nucleus as one thing, as one entity. You're not interacting with all the other subcomponents. And you can see this is what people used to call, or still call, spin-independent interactions. Those are the ones where you talk to the whole, every nucleon in the nucleus, and spin-dependent interactions, where you talk only to the spins only talk to each other. And the difference is that one is much, much bigger than the other. So now I put all this stuff now. So I cleared the clutter. I just want to show you here that there's a very low energy scale where you write down interactions with the nucleons. That's the lowest thing that you should reasonably do. And a very high energy above lambda, where you have a specific UV complete model that describes your everything, the dark matter interacting with the standard model. And below here is a very general, it's very general because it's just an EFT and just the very relevant degrees of freedom, and it captures a very large class of models. So the question is, what should I do? No, I want to be general, obviously. So I want to be as general as possible. So what can go wrong? Well, things can go wrong because, as I will show, when you're very general, you lose information. And this information could be important. So you need to choose wisely. And if you don't choose wisely, you have to be careful. So this is the introduction. And I thought that maybe the best thing to do from the next step is just to take one concrete example and go from the very top to the very bottom or the other way around and see what happens, what could go wrong, etc. So maybe it's a good time to pause and see if there are questions or.
Yeah, we've been following.
Sorry?
It seems people have been following, unless there are
Okay.
questions. Or
Okay, very good.
We've been interrupting with our questions. All of a sudden.
Very good, very good. It's excellent. Thank you. Okay, so let's talk. Let's think about a Majorana dark matter. This is very simple model. All I add is a Weyl fermion. So this Lagrangian is only in terms of Weyl degrees of freedom, and I only interact with the right-handed fermion. So this is all the fermions here are just in the 0, 1/2 representation of the Lorentz group, and the sum over F here, this fermion that has gauge interactions, it is the up type quarks, down type quarks, electrons, charged leptons, and this dark matter candidate. And I'm only talking to one generation of them. Because I'm only talking to right-handed quarks, there's no flavor problems with this model. I don't induce flavor violation. This model is anomaly free with the following charge assignment. So it's essentially a UV complete model. There's no problem here. It's unitary, it's gauge invariant, all that stuff. And after spontaneous symmetry breaking, since this chi fermion does not carry any other conserved charges, continuous conserved charges, let me say, because it's possible it has probably wanted to have Z2 symmetry. And you see that this Lagrangian is indeed invariant under the Z2. It gives you a Majorana fermion. So it's just one Weyl fermion, 2 degrees of freedom. It's self-conjugate. It doesn't carry any charges. Okay, so let's start from the very bottom. In anticipation of what this model gives you, it interacts at this very low scale that I mentioned before, this non-relativistic effective field theory, with 4 operators. The very first one here is the spin-dot-spin interaction that I mentioned before. This is what people used to call, or people do call, spin-independent interaction. But you see, all I misspoke, spin-dependent interactions, because they depend on the spin. You see, all of the interactions here depend on the spin. So all of them are spin-dependent, but they all come with different factors. But this here comes with spin-dot-spin. This one comes with I have to make a scalar out of these operators, and this is the Galilean invariant theory here. So I can take the spin, which is a vector dotted with another spin. Oops, sorry. I can take a spin, which is a vector dotted with q over mn. Q is the momentum transfer, and I have to do the same on the other side. I can dot it with the velocity. When I dot it with the velocity, actually, what happens is that on the other side here, you can put the number, the number operator 1. So this one is coherently enhanced because it has a 1 on the nucleus side. So always here's the dark matter current dotted with the nuclear current. And so here it's just 1, so it's coherently enhanced. And then here, 09 is spin dot q cross n, whatever. So, so these are the operators that appear in this setup. And if I go one step up, which is now this NF equals 3, so this step is above the threshold of QCD, so of the confinement scale, sorry, so that the degrees of freedom are quarks and nucleons. So what do I have here? I will explain this A. I just didn't want to write a whole bunch of equations, so I have the shorthand and I'll explain what this means. This A means it's an axial vector current. An axial vector current is some fermion psi bar, gamma mu, gamma 5 psi. So it's just an axial vector. Gamma mu, gamma 5 is what makes it an axial vector. So this is on the dark matter side. I always write dark matter on the left and standard model on the right. Dotted in this case, Lorentz contracted with an axial vector current on the standard model side. And this depends on the up and the down flavors. So here I have up, down, and strange. I've ignored the strange because I have 3 flavors here. I've ignored the strange because its contribution to direct detection is very small, and I want to keep the problem simple so that we can explore it. It doesn't, if you turn it on, I promise it doesn't add anything to the story. And the other operator is again axial on the dark matter side. So I can only have, so for a Majorana fermion, because of charge conjugation, I can only have axial currents interacting with I can only have axial vector currents. Vector currents vanish. This is a property of the Majorana fermion. On the standard model side, I can have both axial and vector, so that's what the other one here is. So it's axial current on the dark matter side, vector current, gamma mu only on the standard model side. So you see what happens when I go one step up, these operators, which I would, and they do, in fact, dark matter experiments do treat these as independent parameters. They are in a sense independent parameters, but they're never independent in any model of dark matter. They're not even independent when I go one step up and not even think about a model, but match from this theory with quarks and gluons onto this non-relativistic EFT. They're correlated. This line means contact interaction, and this line means there's an exchange of a meson, a pion. I will show this example later. And these are contact interactions again.
Sorry, Fady. So these
numbers
that's the order of the.
Oh no, sorry. That's the number of the operator. It's a very bad. Sorry. This is the operator. Operator 4, and R means it's in the non-relativistic EFT because they're on. And below the operator is the actual interaction. What this operator looks like.
I see.
So this is just the nomenclature, the name of the operator. There's a paper which I'll mention later where they numbered these operators.
Okay.
There's 14 of them at this order and this kind of stuff.
So
but
these
only
are
4
all at
here.
the same order?
They are all, thank you, yes. They're all the expansion here is for up to a spin 1 mediator that would generate these operators and up to momentum squared. So in higher order in momentum, you would have more operators and so on. And if you have a tensor interaction, then you would generate more of these. And in fact, we show at some point in one of our papers that if you consider next to leading order currents, you would generate more of these operators. And in fact, they stop being Galilean invariant after this order. So they're only Galilean invariant at this order, which is not a surprise because there's no reason to expect that a Lorentz invariant theory matches onto completely Galilean invariant. There's no reason for this to be true. So, but at this order, it is true. And then if you go one step up, now I just skip a bunch of scales and I go to the electroweak scale. So this 6th flavor above the electroweak scale, then I would have to write in terms of left, because no, standard model is a chiral theory. So I have to write in terms of left-handed currents and right-handed currents because they're not the same. So now A is the same as before. Left-handed here now means gamma mu times the projector P left, and R means gamma mu times the projector P right. So this is a left-handed current, this is a right-handed current, and the right-handed current, so the left-handed current, I cannot distinguish between up and down because they're unified inside the doublet. A right-handed current, obviously, there's a right-handed current for the up and for the down. So now you see I have 4 operators here. They're matched onto by 4 operators here in a correlated way. And these 4 operators here, so there's 4 because there's this current axial times axial for the up, axial times axial for the down, same here. So there's 4. They're matched onto in a very correlated way by 3 operators in UV. So this is not surprising. Obviously, you know, if you think about this, you know that a full model matches onto an effective field theory in a very specific way. It's not a general. So the operators will not be independent parameters. And the more you go up, the more correlations you see. The reason why I stress this fact is because you might be tempted to this is the dangerous part. You might be tempted to treat these operators here at NF equals 3 as independent parameters. But if you do this, you risk violating gauge invariance. So you could violate gauge invariance because these are not the standard model theory is a chiral theory, and you have to put them back in a doublet and a singlet current. And then finally, at the very top of this this tower, you have this this model, which again, of course, matches onto both of these operators in a correlated way. So this is just to show that why do you need effective field theory? You need effective field theory because at each scale, there are relevant interactions, there are relevant degrees of freedom, and there's a power counting parameter that comes with this thing. The power counting parameter, as we just discussed, is, for example, in this case, Q over Mn for this theory. So I want to write down all the interactions up to Q over Mn. And Q, if I remind you, Q is 200 MeV. Mn is the mass of the nucleon. It's 1 GeV. So this is a 20% expansion parameter. It's not so bad. In fact, this is the expansion parameter of chiral perturbation theory. So this is indeed actually what, between this step and this step, we write down a chiral perturbation theory because what's a better way to describe the interactions between an external current, like a dark matter current, and pions and nucleons and baryons, and pions and baryons and other hadrons. So this is a power counting parameter of the EFT. So here, this Galilean invariant theory goes up to order Q squared over Mn squared. So at this order, you get 14 operators. If you increase the order, you get more operators. But because this parameter is small, and if nothing goes wrong, then I will be the cross section will be dominated by the contribution of the first 14 operators that go up to Q squared, and the ones that go to Q to the 4th will be subleading. Same here. The expansion parameter here would be something like the cutoff of the theory. Let's say the cutoff is the electroweak scale, because above the electroweak scale, I start seeing other degrees of freedom. So as long as you don't have anything, you describe all the degrees of freedom up below this scale, then this gives you a power counting in these parameters. And this is what flavor physicists have been using for many decades. This is the weak effective theory below here. And above here, this is what you might have heard is called the SMEFT. It's the standard model effective field theory. And again, the expansion parameter is something like energy divided by the scale lambda, which I showed before, which is something in a TeV range. So these are the effective field theories so effective field theory allows me to organize these interactions. And in principle, these coefficients are independent, but you have to be careful. That's the point of the slide, of this story. You have to be careful. Remember, I said that you want to be as general as possible, but you have to be wise about it. You cannot. You have to be careful that you don't make a mistake. And by the way, it might seem like a silly thing to say, but it has happened that people have in the literature have violated, unknowingly violated gauge invariance and saw some big signals and claimed that there would be mixed signals, etc. But of course, you have to be very careful. Okay, so let's talk about these independent parameters just in a little bit, make the story a little bit more concrete, and then complete the UV model so you have some global picture of what's going on. So 3 operators in the 6-flavor effective field theory, this is the standard model effective field theory, match onto 4 operators. So obviously these 4 are correlated. Here's these 4 currents that I wrote earlier: axial times vector up, axial times vector down, axial, axial up, axial, axial down. These are the Wilson coefficients of these operators. Just forget about the hat and everything. It's just, I wanted to use this C and a very curly C to just distinguish between the operators in this theory, which have the very curly C, and the operators in this theory, which have the not so curly C. The superscript 6 here just is the dimension of the operator. It's a dimension 6 operator. It's a 4 fermion operator, just like in Fermi theory. So it's a 6 dimension 6. Okay, and so when you want to think about pure, in this case, people used to think about pure spin-independent interactions and spin-dependent interactions. The spin-dependent interaction would be just this one operator, but you see that this model does not really fit into this one operator by itself. It matches onto all 4 operators, and it matches onto all 4 in a correlated way, and some of these operators are coherently enhanced. So this simple picture is not so easy to implement here. So let's say I want to just generate the coherently enhanced operator, which is 08, which comes from having a vector on the standard model side. Is it possible to do this? Yes, it is possible. But if you want to do this, you cannot violate isospin. If you violate isospin and do this, isospin meaning that the coefficient of the up and the down is different. Remember that in the full standard model, the up and the down, the left component of these fields have to have the same coefficient because they unify in one doublet above the electroweak scale. The right-handed ones is okay; it's free. You can mess with those. But if you want to generate only one sort of interaction, you need the left and the right to conspire to give you this interaction. You cannot just make a vector interaction by just switching the up and the down right-handed fields, the right-handed coefficients. You need to do both. And if you do that, then it fixes all of them, and you cannot violate. If you do this and then violate isospin, meaning coupled to the up and the down in a different way, then you violate gauge invariance, and there's no question that you're done. So if you want isospin violation, then you need to only set 1 to 0. Why do you want isospin violation? I will show you later. Let's simplify the problem a little bit more. These 3 coefficients in the 6-flavor theory are independent parameters. These are really truly independent parameters unless you have a full model. Okay, so at least if I treat them independently, I won't violate gauge invariance, so I won't have any problems there. So they come with some, let's say it's tree-level matching, just like Fermi theory. So like in Fermi theory, you have quarks interacting with a lepton and a neutrino and a W intermediate. So the amplitude has 2 W couplings that comes as G prime squared. It's divided by the W mass squared, the propagator, which you take the mass much greater than the momentum, you get MW squared. And the cosine theta is just to parameterize this as a, just going to spherical coordinates, just to describe these 3 directions. But I will make sure that the sum of the square sum of the 3 of them is 1, or G squared, sorry, the G fourth over lambda the fourth, which means that I removed 1 variable. So now it's a 2-dimensional plane, and then I'll look at a 2-dimensional plane. So let's look at this 2-dimensional plane. The connection will be lost, I know, because you can keep all this in mind, but just remember that these 3 coefficients are now described in this 2-dimensional plane. So varying theta and varying phi gives you different amounts of these 3 coefficients. Okay, that's all you have to keep in mind. So varying theta and phi gives you, and there's a correlation between all 3 in the fact that I kept their square sum equals to this quantity. So what is this plot? So theta, I normalize it by pi, and phi, I normalize it by 2 pi. So this thing goes from 0 to 1. And I plot contours of the overall normalization of these contours is irrelevant. The relative size of them is what you care about. Okay. And this is the relative direct detection rate between in this plane. So it means if I dial theta and phi, I get here in this yellow contour, I get a direct detection rate of 2 in some arbitrary units. And if I dial them in a certain way, I can go below 0.1. And in this very small circle, it's 10 to the minus 2 or so, 10 to the minus 3. Okay, so I can vary by 3 orders of magnitude by dialing theta and phi. Okay. Now, remember that these theta and phi are in principle completely independent parameters, because this standard model of these are coefficients, Wilson coefficients of the standard model effective field theory, and they're completely gauge invariant. There's no problem. So you think that this whole plane would be fine, but it's not. So I'll show you why in a second. But here I just show you the isospin limit lines. They're right here, these two, where the up and the down coefficients are equal. And these stars just correspond to some models that we chose in this plane. So now I overlay on top of here anomaly freedom condition. So I want to build a full model. Now, the only places in this plane that under certain assumptions, okay, you can relax the assumptions, but the picture doesn't change very much. You are not able to easily populate this whole plane. So you have to live on this dash. So I go back, so the dashed lines disappear. Now the dashed lines are back. So on these dashed lines here and this curve, you can have models that are free of gauge anomalies, which in the end, this has to be a model of dark matter. So in the end, it has to be free of gauge anomalies. So you see that even in the theory where these things are really independent, they're still not really independent because you need to worry about this issue. So the moral of the story here, what I'm trying to get across is that effective field theory is the right description for this problem. There are so many scales, but choosing which effective theory you go to is important, and you have to keep in mind UV considerations. And this has been ongoing, been a shift in the community, thinking more and more about these UV models rather than just effective operators, or worse, what people were thinking about for some time, which is simplified models, which I won't mention. So taking a 1D slice of this 2D plane that I showed you above, so theta equals, sorry, yeah, please.
Can you go back 2 slides? Just I wanted to before you just to understand your parameters. You've given us you've given us a mountain climbing exercise here to understand the geography.
Oh yes, I'm sorry. I just
And I'm just really slow. So
no. I went too fast and I didn't expect all this.
No, that's okay. I just wanted to check that you. Yeah. Okay. So now, I mean, I didn't quite understand why there's just one anomaly-free curve there, because surely that's model dependent.
Yes. So the anomaly-free curve. So yeah, good. Okay, I can explain. So in a model, you match onto these operators. Sorry, did I show this model?
You did.
I showed it here. Sorry, I'll go back to the model. So anomaly freedom tells you what the charges and up and the down are. They're fixed by anomaly freedom. So for a fixed charge, I can only have certain amounts of these coefficients, because I didn't tell you what these coefficients are. I did say them well, actually I did tell you, but in a not so, maybe not so. So yeah, okay. So one of them is the coefficient of the axial vector current on the dark matter side times the left-handed current. That would be the current with quark doublets. That's C6(1) here. Then the other two are the coefficients of the right-handed currents, right-handed up current and right-handed down current. And that would be 7 and 8. So 6, 7, and 8 are the coefficients of these operators. These are the three that I parameterized here. So anomaly freedom correlates the Wilson coefficients of these operators and give you specific values of them, which means that it constrains where you can live in this plane.
Yes, that I understood.
Yeah.
But it surprised me that there was only one curve there. And then,
So this is under. So this one curve is for this model indeed.
Oh yeah. Always say okay. So it is only just for this model.
Well,
then I'm happy.
No. The model is one point in this plane. Sorry, the model is one point. The curve is a family of models, but under the assumption that you only charge right-handed fields, then you get this. So if you start adding left-handed fields, then the anomaly conditions become more complicated. But still, it's a curve, and then you can live on one point in the curve. So I thought at some point that you can make an infinitely dense set of curves on this plane and populate the whole plane, but it's not possible for rational charges. And this can.
Sorry, Fred, I have a question. So
yeah, please.
I think you're probably going to explain it more, but just to make sure I understand this plot well enough. So, like, if you're on the, let's say, yellow curve with coefficient 2, does that mean?
Sorry. This is not the coefficient. This is the relative direct detection rate.
Okay, yeah. So that's what I meant. So that means the direct detection rate of a model that has a certain Wilson coefficient is going to be twice as large as the direct detection rate of a model that has.
This one, yeah.
I see. Okay, yeah.
And 1 to 2 is not the big deal. The big deal is that you can go to 10 to the -3. Yeah. So it's 3 orders of magnitude suppression if you can manage to go here.
Okay. So then if you want to kind of overlay the experimental constraints on this one, you would be, let's say, ruling out the large numbers.
I'll show you actually the experimental constraints. Yeah, that's actually the slide here.
Good, thank you.
So what happens here is that you have, so when take a 1D slice of this 2D plane that we have, one for fixed theta, one for fixed phi. So I'll go back one step to show you where these two curves are. So phi equals 0 is this bottom dashed curve here, and theta equals pi over 2 is a vertical line here. Okay. So what happens is that because this model matches onto both these axial times vector and axial times axial in a correlated way, then you get, and if you look at just the axial, one of these curves by themselves, you see that it has these big dips here. But because you have to add the other curve, you have no choice. It also has dips, but the dips are in different locations. So unless you can make these dips align by some model, you cannot cancel this rate. And why do you want to cancel this rate? You want to cancel this rate because already for this model, this right-handed model that I showed you, if you look at the bottom here, this is a function of the dark matter mass. And here is essentially on the y-axis, it's just the mass scale. It's 1 over the square root of the Wilson coefficient, which is, the Wilson coefficient has dimensions of GeV to the -2. So 1 over the square root of that is units of GeV. And that's essentially the mass of the mediator that makes this interaction. You see that already, the direct detection, which is this red curve, not the dashed one, but the solid red curve. This is xenon 1 ton. This is the curve that I showed you above. If you recast it to this plane, it rules out mediators up to 3 TeV. Okay, this is already for this Majorana dark matter model, which people thought, 5-10 years ago nobody would have cared about this because the rate of this model is so small that you wouldn't have, it's not being probed, but now it's being probed. Allowing yourself to make a model that lives, a consistent model that lives in some of these troughs here, allows you to reduce this pressure down to down to 600 GeV or so, 500 GeV. So that's why you want isospin violation, because without isospin violation, you can never get to this point, to a point that is suppressed enough in direct detection. So this model is completely consistent. It's anomaly free. It's going to be probed by these. So the white gap here between this yellow curve and this red curve. Sorry, the dashed line is the projected xenon bound 20 ton. That's 10, 20 years, 10, 15 years, let's say, in the future. This blue curve here, which is the same as the blue curve here, is a bound from the LHC. So this is now, you see the full complementarity between search strategies, between the LHC and direct detection. The yellow band here is the mediator, not producing dark matter at the LHC, but producing the mediator, and the mediator decaying to tau jets, because this model requires coupling to leptons, and you couple to the ditaus. If you couple to electrons, you're ruled out because the signal will be too strong. And for the green one here is dijet, so producing two quarks, and then the quarks hadronize into jets. So you see there's these bands are exclusions from current searches at the LHC. The solid line is exclusion from current direct detection experiments. And what's allowed is here, and this will be pushed up. Probably there will be search strategies to cover down in this area, and this gap will close in the next 10 years probably, or at least get more constrained. But we have a very simple model that allows you to live here, and all these considerations of the correlation between the coefficients have to come in, have to be considered in order for you to make this model. So
if I may ask a question.
Yeah, please go ahead.
So the applicability of these bounds of di-tau, dijet, this also comes from the charge assignment that you had in the beginning, that if,
absolutely,
for example, if you couple to mu's, then I guess a di-mu bound would be stronger. I see.
Yeah, absolutely. If you couple to electrons or muons, the bounds are much stronger actually. So you see, you already have to play even some games too, but reasonable ones, not unreasonable ones. Coupling to one right-handed, the one generation of right-handed lepton, or any one generation of right-handed quark or lepton is okay, because you might worry that the mass bases and the gauge bases are misaligned, and there's no notion of which one you're coupling to. But for right-handed rotations, it's possible to do this actually, and you can do this. If you start talking to left-handed fields, then it becomes a bit more complicated, and you induce flavor violation, in fact, and it's one of the things we look at in this. Well, we didn't discuss in detail, but we thought about.
I mean, charge lepton flavor violation is very constraining, but it does still leave you some room. So
I'm worried about quark neutral.
That's
neutral currents in the quark sector. And indeed, it turns out even if you break the symmetry between the first generation and the second generation quarks, if you don't couple to them universally, then demixing puts a very strong bound of something like 50 TeV on this mediator. So there's also flavor constraints that one needs to take care of. But if you keep the symmetry, then this essentially disappears. So
absolutely, And so in the top right plots, you're showing a model with isospin violation, and that's a viable model, right?
Yes, this one is actually living on this anomaly-free curve here. But it requires that you charge the left-handed quarks, and if you charge the left-handed quarks, then you have to be very careful about flavor violation. That's the So if you just only charge right-handed fields, then it's flavor violation is not a big concern. But if you start charging left-handed ones, then you get in trouble, because then you don't have the freedom of the rotation matrices anymore. You're forced to have some flavor violation. It's not possible not to.
Fantastic, thank you.
So I have some additional examples, but I see that I'm already at time, maybe already even over time. Should I just go to the conclusions, and then if you want, I can go through the other examples? Is that the best thing to do?
I mean, usually we're not bound by time. I mean, some of these seminars have gone on for 5 hours. So.
Oh dear. Okay. Well.
As long as you have the energy, and I guess the audience has the energy.
Okay, so should I just go to my conclusions, and that way people are sort of, and then I can come back to this after that, or should I just continue? I don't want to.
I mean,
whichever works for you is fine with us.
Okay, if you don't mind, then
maybe going to the conclusions works for some people.
Yeah, that's good. Okay, let's do that. Yeah, I think that's better. So, so just to summarize what I said. there's overwhelming observational evidence for the existence of dark matter. This is mainly from gravitational interactions. It's reasonable to think that it's a particle in nature, and if it's a particle in nature, we want to discover the model and disentangle the structure of the dark sector. And this will only be possible if you look at multiple probes, and these probes come at different energy scales, and you need to connect them in a consistent way. And the way to do this is with effective field theories. This is the classic setup for effective field theories. We have a public code called DirectDM that implements all this stuff, this running and this matching, and all you have to do is match, so provide the Wilson coefficients of one of the effective theories in that tower, and then it does everything else for you, and it matches up onto the nuclear form factor code directly, and then you can just compute the rate without too much trouble. And this was traditionally done in the past. People would convert the dark matter cross-section to dark matter nucleon cross-section, spin-dependent and spin-independent. There's no really need to do this. You can compare directly on these plots that I showed you, which is the mass of the mediator versus the mass of the mass of the mediator on the y-axis versus the mass of the dark matter, the gauge coupling, or whatever you want. And people have been doing that recently. So it's just a better way to compare things. And yeah, that's what I wanted to say.
Maybe we can take some just general questions from people.
Yeah, please. Yeah, absolutely.
We can go back and understand the other things.
Sorry?
We can then go back to
yeah, absolutely. Yeah, general questions, welcome.
Maybe one general question that occurs to me is that it's hard to imagine that there's it's hard to understand whether there's an upper bound on the mass of these particles of dark matter, for instance.
Yes.
I remember a seminar of Holger Nielsen where he was claiming that there could be enormous mass, which seemed almost absurd, but it would look very difficult to rule it out.
Yes. Okay. So that's a good question. Actually, it's a very good question. There is a so-called unitarity bound that at some point the cross section becomes so large with the mass that it violates unitarity, which means that the probabilities become bigger than one. But people have found loopholes to this, and maybe that's what you were mentioning, that the masses are enormous, like I don't know, 100 PeV or what, I don't know, things like this, like crazy masses. There are some workarounds. If I remember correctly, this unitarity bounds roughly, if you don't do any gains, put an upper bound on the dark matter mass of 200 or 100 TeV, let's say. But that's even already too large.
And how are those dark matter bounds? How is that unitarity bound obtained?
Yeah, good question.
I think the eigenvalues of the S matrix scattering become too large.
Yes, but how does it it enters because
I mean, the fact that you're putting in a bound on the mass through that is what's surprising.
The mass of the what? Sorry.
Of the dark matter.
Yes, indeed. It's on the dark matter mass. Essentially, it's okay. I don't want to say. I don't have it in the back of my. Yeah.
There must be some additional assumptions being put into the structure of the dark matter to get something like that.
Yeah, there probably is. No.
Yeah, I mean, from
few assumptions.
From relic density, you already know. Well, you know.
Oh, that's a different story. Yeah, that's a different.
But yeah, so if your dark matter is too light, then you need a large number density. If it's too heavy, then you need a very small number density.
But we don't know the number density, so.
Well, if you know the mass, then you know the number density.
Yes, but we only know the gravitational aspects of them. So the two are coupled. One goes up, the other one goes down.
Yeah. It could be what Venus is saying is that the cross section has to get super large in order to. That's probably what it is.
Yeah, that's exactly what happens. I mean, this cross section got huge.
Right.
But
that's
But can we really rule that out?
experimentally, I mean, it's very hard to, as far as I know, I don't know how you can probe such a large mass dark matter anyway, because that's not going to, I mean, this you can only do in astrophysical probes. You cannot really do in laboratories at the moment. So
Yeah.
It must be like a signal, like a maybe annihilation signal or something that you would see super high energy. Because if you have these things annihilating with each other, even though their density is so small, maybe it still can happen, and you would have some spectacular burst of photons coming from, maybe neutrinos. I don't know. Maybe there's these high energy neutrinos that people were trying to find, and I think people even propose such dark matter models that decay to these neutrinos and or annihilate into these neutrinos. Dark matter can decay, just the lifetime has to be super long.
Yeah, I think a very heavy dark matter mass doesn't agree with, is it small scale structure or? Yeah, but you're right.
It could be, yeah. I mean, you probably need a higher enough density that yeah, I guess probably at some point the density is so low that you cannot.
It becomes very difficult.
Yeah,
it's very challenging situations that way. Okay,
yeah.
I don't want to dominate it. Are there other questions? I noticed Werner is there.
Yeah. You talked about astrophysical constraints. Now, for example, if you have galaxy collisions, then you might get velocities which are larger than what you have here. So you might get constraints on some of the interactions. What has been done in this direction?
Yeah. So indeed, actually, if I go back to this picture of the bullet cluster. That's what you have in mind, I think. Something like, oh, it's stuck. Oh, here we go. I should have probably one more. So the bottom left here, I think, is what you have. So this is indeed a collision of two galaxy clusters, and the blue haze here is the weak lensing, which shows you where the dark matter is. Mass, and this is the other one here, and the red is the X-ray from the interstellar medium interacting with each other and making shock waves and heating up. So this is in the X-ray. This picture is a composite of visual, weak lensing, and X-ray, and indeed a study of these guys. I'm not sure I'm answering exactly the question you're asking, but please tell me if I'm not. So indeed, a study of these sort of galaxy cluster. There's about, I don't know, by now maybe a bit more than 30 of them observed, and looking at the offset between sort of these interactions, they can put a bound on the self-interaction of dark matter. And this at the moment is an upper bound, and the upper bound is something like a barn. A barn means neutron-neutron scattering cross-section. So it's a very, very large cross-section. What would be interesting if they put a lower bound, because if they put a lower bound, that means that you have to have some self-interaction beyond gravitational interactions. That would be a very nice signal for particle dark matter. But I'm not sure this was exactly what you were asking. Is it?
Well, there's dark matter self-interaction, and also obviously the dark matter is not braked too much by the ordinary matter. So
you mean that the velocities would be so high that some?
Yes, I don't know how high.
I think these velocities are still quite small. I mean, they might be. I mean, these galaxy clusters are. I don't know exactly how fast they're moving, but I don't think they're moving at a very significant fraction of the speed of light or something like this out there. I don't know exactly relative to each other. I think the velocities are still low, but okay, I don't know. I don't know exactly what the velocity between them is.
Yeah, thank you.
I think they're low enough that there should be nothing. Yeah. You're worried that the velocity is too high, right? That's the issue.
Yes. Yes,
Yeah.
yes.
I don't think so, but
Well, I wanted to compare the velocity for these collisions
yeah,
with velocity for the rotation of the galaxy or so.
right. No, that's a good question. Yeah, it's definitely a different scale. Absolutely. Yeah, it might be. It's certainly probably higher than 10 to the minus 3. That's probably for sure. No, I mean, there's no really reason for that to be, because 10 to the minus 3 is more characteristic of the you know, sort of the Maxwellian velocity distribution with this cutoff at, you know, with this in this galaxy, and this sort of comes from n-body simulations, and it's consistent with observation, but it's a characteristic of being in this halo, and obviously these two things are moving towards each other, and there's no, so certainly it's a different scale, and certainly almost certainly it's higher, but I think it's still quite non-relativistic. But I could, I don't know, I could be very wrong about this, so.
To continue on the cosmology theme, do we know much about how dark matter plays a role in physics at the electroweak scale and its phase transition or inflation?
Oh, in inflation for sure, because, well, at least in the sense that, okay, so you want to see, is there an interplay between dark matter and electroweak phase transition? You mean to make the electroweak phase transition first order and to generate to make baryogenesis or leptogenesis? Is this what you have in mind?
Yeah,
Or,
I guess we know that the electroweak phase transition in the standard model isn't doing quite what we want. So
yes,
if dark matter could help alleviate some of these problems.
certainly you can build a model where you have, I mean, people build models where dark matter is sort of carries the missing or the other part of the asymmetry in the baryon asymmetry, and you can certainly do CP violation in the dark sector and share it with the visible sector. So this is this is something that you can do indeed. So you can do it this way to affect the electroweak phase transition, make it first order. The models that at least the work that's been done recently, as far as I know, it really mainly focuses on adding scalar to the Higgs potential, you know, adding scalars interacting with the Higgs potential. There are models where you try to add scalars and fermions, but I think you need scalars. And this could be dark matter. I don't think it would depend on the model, right? And these numbers of scalars are very large, actually, in order to really make the Higgs potential first, or you know, support a strong enough first order phase transition in order to make this large number of scalars is something like 200 or something. And there has been work by a group at DAISY, the group of Géraldine Servan at DAISY doing this, and I think also a paper by Riccardo Rotazzi at some point looking at this. But you need scalars. You can do it with fermions and in addition to scalars, and the scalars could be dark matter. I suppose it depends on the model and whether they need to have a VEV or not, and I think some of them do. So.
So
Yeah.
If I may add to that comment, so actually, you don't need to have that many scalar degrees of freedom to make a first order phase transition work. I mean, in a 2x double model, it is possible to do it, but you're pushing your couplings of the scalar potential to the non-perturbative values. But yeah,
I mean, large number of scalars is also the same. I mean, it's the same game. I think you're right. Yeah. Absolutely. Yeah. I mean, also having 200 scalars means you're in a non-perturbative regime, I think.
Yeah. So anything beyond the 2x double model, it is possible to make the electroweak phase transition first order, but that is assuming that the dark matter particles do contribute to the electroweak phase transition.
I mean, they still have to couple to the Higgs in a certain way to modify the potential, and
that's for sure. Yeah.
Whether you do it with a large coupling or you do it with a large number of scalars, that's equivalent in a sense.
Yes. But
I don't.
just as a side answer to Jasmine's question, so first order electroweak phase transition is needed for electroweak baryogenesis. There are other kind of mechanisms of baryogenesis which don't necessarily need a first order electroweak phase transition.
Yeah, for example, you could do it indeed as the question was asked. You can do it with a dark matter model that has CP violation within the dark sector, and then somehow you share it with the standard enough CP violation, and you share it with the standard model via some baryon number interaction type thing.
And with inflation, I'm guessing you'd be beyond the perturbative or at least effective field theory regime if you're looking at Planck scale physics. So.
Yeah. Not necessarily, but yeah, it depends what you want to do with your model and what are the degrees of freedom of your model.
Yeah, I mean, certainly to have effective interactions that are suppressed by the Planck scale, then you I don't know, you need, I'm not sure actually what you need to do to make those relevant. And
just one other quick question.
yeah, please.
You briefly brought up non-particle explanations for dark matter. Is this just sort of like modified gravity, or are there more things here?
Yes, there are more things there, actually. It's not easy, and they have been squeezed. So one thing that used to be talked about is these machos, these massive compact halo objects. So something like maybe not neutron stars, but things like this, bigger objects that are compact. These are ruled out. I think it's difficult to make that work. Primordial black holes could be a component of dark matter, even though I think it's not so easy to make it all of dark matter, but that's also an area of active debate. So something like this, with this, purely made of standard model particles and only gravitationally interacting. Modified gravity has problems explaining some of these observations. Famously, this bullet cluster type physics is hard to explain with modified gravity, but maybe there are ways to get around that. I'm not 100% sure. I think, if I understand correctly, the status of these modified gravity models is they need an additional component of dark matter. You cannot just do it with modified gravity. And in that case, then, well, it's not the explanation for dark matter. At least a component of it. What else can one do with non-particle? Yeah, I don't know. I think these are the ones that come to mind.
Could cosmic strings play a role in this?
As dark matter candidates?
Yeah, I'm not sure what the status is of them, but it's just a thought.
Yeah, people study, actually. That's also another. I don't know much about. That's not something I know very much about, but there's been an active debate about how to model these string networks and how they interact with each other and decay in the context of cosmology. Maybe dark matter, I don't know how the connection would be, but certainly it's an area of that people think about what they can be. I think more in terms of bubble nucleation and gravitational wave generation. So these collisions between cosmic strings, and people have been studying these on lattices and things like this to do a better job than modeling the string as a infinitely thin object. But as far as dark matter, I don't really know.
Okay, thank you.
Could you hear some of the other examples?
Sorry?
Do people have energy for the? Do you hear some of the other examples, or do you have?
Oh yeah, sure. So let's see. Maybe the best
Just nice,
is to go.
nice to just see them briefly.
Yeah, sure. So one example would be an operator that's so now all these operators that I'll show are in this so-called standard model effective field theory, and then we augment it by dark matter current. So you have a dark matter current attached, locally interacting with the standard model current. And this operator here is so it's an axial scalar current, a pseudoscalar current, sorry, of dark matter interacting with GG dual, and G here is the field strength tensor of PCD. So how could you generate this operator? You can generate it very simply by an axion-like particle. So if you have an axion, but it has to be heavy, would generate this interaction. So one thing that doing things properly in the effective field theory and taking care of all the leading contribution is to take care of the pion exchange. So typically what people have done in the past is take care of the contact interaction, but there's a pion exchange because of the nature of this pseudoscalar nature of this interaction. The dark matter interacts with a pion, and the pion interacts with GG, or interacts with the nucleon effectively. And you can see this by the pion pole has a momentum dependence in it. So if you set this to 0, then it's effectively you turn off the pion pole, because also I think momentum also comes, it's something like q squared over q squared plus m pi squared. And so if you set q squared to 0, then you turn off this interaction. And you see if you do that, this is sort of the direct detection rate, roughly, in arbitrary units. So you see this dashed curve, and then if you turn on the interaction, you see this black curve. And the difference is a factor of 10 in some mass ranges of dark matter. And it's instructive to actually see this in terms of, I mentioned earlier that typically these experiments have a sensitivity window between 3 and 50 keV or 40 keV. This is the recoil energy. This is the spectrum that they integrate over. So Lux, which is similar to Xenon that I showed, has this window, so between 3 and 50. These interactions the momentum-dependent interactions tend to, of course, dominate at higher momenta, which translates to higher recoil energies. And so if you can integrate more, you can expand this window, and they are doing that. And indeed, it's very difficult because the backgrounds become very hard to suppress at such large recoil energies. Then this interaction would be even more relevant, that you need to keep this into account. And here is to show you this. So this is the recoil rate. Again, this is some direct detection rate the spectrum. And the blue curves here are the Xenon curves, and the dashed curves here are fluorine curves. So this is now a nucleus that's 10 times less massive, let's say. And this is the PICO experiment I think I briefly mentioned. And that one can go up to higher momentum recoils, but because the mass is small of the nucleus, the effect is not as large. So that's one thing. So full momentum dependence is an order 10 effect. We're interested in not order 1 effects, because there's so many. Order 1 effects will be useful once you have a detection and once you have other uncertainties under control. There's astrophysical uncertainty in the velocity distribution of dark matter, in the local density of dark matter, all these things. And there's, of course, uncertainties from the nuclear physics side, computing these form factors. So order 1 effects are not important, but order 10, order 100, those you want to keep. Another example of this correlation that I showed is if you have this is a super motivated, super simple model of dark matter. If you just have electromagnetic dipole interaction. So dark matter does not have a monopole, it's not charged. It could be charged, but this charge has to be very small. It has to be milli-charged, 10 to the minus 3 or smaller. Otherwise, it is ruled out by many signals, astrophysical signals. So dark matter it can have a dipole interaction with a photon. So this is the field strength of the photon, and this is easy to generate in a model where the mediators carry electric charge, and then this is the only thing you can do. You cannot have a tree level exchange. This has to be generated at the loop level. If the mediators have electric charge, the dark matter is neutral, then this is the only thing you can do, and you can do it like this. This matches onto 4 different operators. 2 of them I already mentioned before, this O4, which is spin.spin, and O6, which is spin.q, spin.q. But it also matches on O1, which is the spin independent operator, that when people say spin independent, that's the one that they have in mind, 1 times 1. And O5, which is another one that is similar to O8 actually, but sorry, similar to, yeah, some whatever. It's coherently enhanced also on the standard model side, but has velocity. You have to make a vector here, so you take this cross this dot this, and these have to depend on the properties of the interaction, how you build these operators, and you see for dark matter, for different dark matter masses on the x-axis here, and y-axis is again a relative direct detection rate. These operators dominate in different regimes. So unsurprisingly, in this case, of course, the ones that are coherently enhanced in the nuclear side are the ones that dominate. The other 2 are subleading. For xenon, for fluorine, they're not. So this is for xenon here, but they dominate in different regimes. So the one that you traditionally call spin independent, sorry, only dominates for very small masses, and the other one dominates everywhere else. So EFT matching gives you the proper correlation between NR EFT operators, and the message here is that probably one should not treat these non-relativistic EFT operators as independent parameters. Their Wilson coefficients as independent parameters. That's a bad approximation. At the very least, one should take this matching step, which is still generic, but at least takes these correlations into account. And a last effect is one that comes from renormalization group running. And this has to do with the fact that in order to make an axial, so the difference here is between running and no running. So electroweak running is these curves in blue, and they're the ones at the bottom. Okay, so there's 2 curves on the bottom. The solid and the dashed are for 2 different interactions, and the red ones here are if you include the effect of running. What does running do? Under RG, different operators mix with each other. This is the usual. This is so well known from flavor physics from a long time ago that if you have you can have a mixing with large anomalous dimensions, and you can enhance a rate, let's say. And this is actually what happens in beta K star gamma. This was discovered at Cleo in Cornell, and it was discovered earlier because there's this mixing from a gluon operator into the beta S gamma operator, and enhances the rate by a factor of 6 or 10 or something like this. So this is a well-known story. Here, the effect comes from the fact that above the electroweak scale, you have to write down in terms of left-handed and right-handed currents. But if you want an axial vector current below, you need a specific combination of the left-handed and the right-handed operators. But if the dark matter is charged under electroweak charges, and this is a class of dark matter models that has been explored, it's not unreasonable, then a W exchange will make so the operator is a 4-fermion operator between dark matter and standard model currents. If you just exchange a W between the standard model legs, between the quarks, that's a conserved current, and it doesn't have an anomalous dimension. What you have to do is you have to exchange a W between the dark matter and the quark, and that only happens if the dark matter is charged under electroweak gauge group under SU2. And if you do that, then what happens is that the operator for the left-handed fields runs, but the one for the right-handed fields doesn't run. So you very carefully arrange the coefficients of these operators so that they give you an axial vector interaction, but this running breaks this alignment, and you end up with a small vector component. Now, the vector component is coherently enhanced on the standard model side. So even if this effect comes at alpha weak over 4 pi squared, blah, 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 no, this small stuff, it's 10 to the minus 2 because it's let's say 10 to the minus 2 roughly. the effect is enhanced by 10,000. So in the end, it's a factor of 100 larger. So you can see here the difference between this lower curves and the upper curves is about 2 orders of magnitude in agreement with this rough scaling that I just told you. So here quantum corrections gives you an order 100 effect, and these are just examples of why you want to do effective field theory, why you want to do things properly, and you want to take care of all the leading corrections. And dark matter this dark matter direct detection story is very complicated because of all these parameters that enter, including this A squared enhancement and the velocity. And I think, and the last thing, so these are the 3 examples I had in mind. And the thing that I mentioned already is this DirectDM tool, which is on GitHub. It's actively maintained by a couple of people, including myself. And what you have to do is just specify the coefficients at some scale, and it computes everything else automatically for you. And it seamlessly interfaces with this DM form factor, which is this package by these nuclear theorists. And this is the paper. This is where this basis, if you want to see this basis of non-relativistic Galilean invariant operators, this is where you have to go to see them, this paper. And this brings me back to my summary, which I already went through.
Just with regard to that paper, how comprehensive do they give the basis of operations?
This one?
Yes.
Yeah, there's 14 operators that
Okay.
If you want to see them, I can show you. I just have to open a different slide.
So you can summarize the whole thing in 14 operators.
Sorry?
You can summarize the entire
Basis.
non-relativistic setting in 14 operators.
Indeed.
Of
course, you have to have some assumption, and the assumption is that you stick to spin 1 mediator, so nothing more than a vector interaction,
right,
and up to q squared.
Up to q squared, and you cut off on dimension, the dimension of the operators. You're not going to get to dimension 100, for instance.
Yeah, I think in this case, if you just stick to q squared, then it fixes you have a finite number. So let me see if I can. Here, this one. Can you see now this screen?
Yes. Yeah.
This is the full basis of these 14 operators at this level. So you can see there should be nothing with more than 2 q's. 2 q squareds in here. So here, this is q squared, and then everything else is so. I think O2 never appears actually. This is v dot v times 1 This I think never appears in any of the models that I've seen. And then if you and indeed, so what happens is it then if you want to go to a higher order in q squared, then so this effective theory, if you can check, this is Galilean invariant. So by shifting the velocities, everything stays the same here. But it is not invariant. It becomes non-Galilean invariant if you go to a higher order in q squared. And higher order in q squared, you want to go to this order if you want to. It's a longer story actually. And it has to do with the chiral effective theory, because the chiral effective theory is an effective theory also in this parameter. So this parameter q over m is the power counting parameter of the chiral effective theory. And this famous Weinberg counting in chiral effective theory, chiral perturbation theory, tells you, so you have the 0th order, the first order, the leading order in q over m counting, then it tells you what for this interaction, what the next order, and for a lot of them, it's not q squared. For a lot of operators, it's q cubed or q whatever. No? So one would think, okay, I don't want to go to higher order in effective in chiral perturbation theory. I want to stay the leading order in chiral perturbation theory. But how far can I go in q squared? And that's sort of what thing that we explored, and indeed you generate more operators here as you expect, because it's higher q squared and they're not Galilean invariant. And the idea that the reason why we wanted to do that is because we wanted to see if you can lift some of these suppressions, like these spin-dependent whatever suppressions, by going to higher Q squared, even though you pay an extra, 20% squared or something. Then maybe you get a huge enhancement. But and indeed, it happens. Actually, you do generate these operators, but they are still suppressed enough that they're not leading. And a whole nother group actually is more focused on higher order and chiral perturbation theory. And for those, you have to think about not just one dark matter current interacting with one nucleon current, but you can interact with two nucleons at the same time. I think I might have this here somewhere. Here, for example, this diagram on the right. So all these are higher order in chiral perturbation theory, and some people, some groups are looking into this. But it's higher order, and yes, you can always cancel the leading order, and then the higher order becomes the leading order, but it's not so. Canceling things is always not so robust, because typically you don't regenerate things. Yeah. So.
Thank you very much. That was a fascinating tour through dark matter physics. We asked you all our burning questions as well. There may be some left. Venus always has some additional questions.
I do, yeah. But I mean, I've made some notes, but they're not really intelligent questions. Just just this whole effective field theory approach. It's quite a good approach. I mean, at the end of the day, whatever model you want to put together, as your code also allows you, you basically just figure out what your coefficients are in terms of the effective field theory and put it in. And they seem to be very, very successful in that, as you said, you don't even need to translate your bounds into whatever dark matter cross-section bounds. You just, already put in.
Really the right tool for this job. I mean, there's other things I didn't discuss, I mean, which is that in principle, the dark matter could be 100 GeV, and your effective field theory could be at 3 GeV, whatever. This third flavor effective field theory. Then technically, this dark matter should be treated as a heavy particle. So we have written down this heavy dark matter effective field theory, because you cannot excite the dark matter. You cannot excite the anti-dark matter, for example. You have to integrate out the mass. So, effective field theory is really, it's all the full range of effective field theories, not quite the full range, but a lot of the range of effective field theories that have been explored really apply to dark matter physics, and it's a very rich application for this.
But I have another, it's not really a question, it's something that keeps me up at night. I mean, obviously, there's no guarantee that dark matter is just a one component particle, right?
For sure.
With multi-component dark matter, do we ever have a chance of detecting it? I mean,
I mean, so are you thinking something like, for example, there's been this idea of minimal dark matter. So what is minimal dark matter? It's just a dark matter that's an electroweak multiplet. It has to be a high enough electroweak multiplet. So something like I forgot exactly what so a septet works, like a 7 of SU2 works. There's a lower one that works. I'm not exactly 100% sure. And because you don't want it to couple tree level to okay. I think I shouldn't say that because that's not correct. But anyway, it works, and that's a multi-component dark matter. So what will happen is you need a certain hypercharge. I think it also cannot be hypercharged. Is that true? Well, it can be hypercharged as long as you have a neutral component in there. This Gell and the Nishishima formula. You need to have a Q equals 0 component, and then whatever hypercharge. So you have doubly charged and whatever singly charged components in there. One of them is dark matter. The other ones have to decay and have to decay to this dark matter. You can detect it. I mean, you can detect. So there have been studies of this. whether the mass is large enough, maybe you can even excite the doubly charged things at the LHC and see them. So it's possible. This is sort of one kind of multi-component dark matter models, but you can have other things where you have a rich sector like flavor in a dark sector. Now, that's another thing that people consider. So a global quantum number that's very reasonable. In fact, I worked on a model like this where you have I mean, one question that always arises in dark matter models is the stability of dark matter. If it's either stable or long enough lived. Usually this is enforced by hand by adding a Z2 symmetry to the dark matter. And so in one of the papers I worked on, we asked the question, can this be emergent from some symmetry? And we considered for this gauged MFV model. So if you take the MFV is minimal flavor violation. It's a hypothesis that says that the only flavor violation in any DSM physics comes from the standard model. If you take the standard model Lagrangian and you set all the Yukawas to 0, this Lagrange is invariant under a huge global symmetry, which is U3 or SU3 if you want, for each the left-handed doublet, the right-handed up, the right-handed down, and the lepton. So there's 5 of these, and the Yukawas break this. So you can break. This is a global symmetry, and there was a model that people considered where you gauge this symmetry. And so in this model where you gauge this symmetry, there are certain representations that you can put the dark matter in that these representations that have so-called zero triality, and these representations have, after the breaking, have an unbroken Z3 symmetry, and the dark matter is charged under Z3 in this case automatically. And so these are models where you have indeed complicated, a slightly complicated dark sector with multi-components, etc. Another one would be, a QCD-like dark matter, which people consider. For example, this dark matter is made of pions that are composite of some hidden QCD sector, SU3 or whatever, SU4. There are interesting things that come from having even N in SUN, where you can have scalar baryons and things like this. So people have explored all this stuff. Indeed, I completely agree with you. I mean, in fact, it's very unreasonable to think that dark matter is just one component, because the standard model is not. No.
Exactly. Yeah.
It's very complicated. So yeah, and Axion, of course, Axion dark matter and many, from string theory. This is not something I know a lot about, but I know it's a very. There are lots of axions in string theory, and some of them can be dark matter, and yeah. So yeah, multi-component is very, very motivated. I think you're absolutely right.
Oh, absolutely. Yeah. And I mean, gravitationally, the secluded dark matter. Then I guess, do we then give up on discovering it? If
people about this, and maybe there is gravitation. I mean, the way to, so if it's secluded like this, then a way to think about it is hopefully it's not just, I mean, probably if it's secluded, it probably has some sort of a, I don't know, it has some sort of and it has some sort of a rich structure. Then people are thinking about what you can do with gravitational, whether gravitational waves or some other gravitational signatures that are non-standard for a sector like this.
Yeah, I mean, but if it is particle, at some point it must have interacted with the, I want to say standard model, but with the inflaton, right? But again, then if you have an inflaton which decays to Higgs and then produces the standard model particles, and then separately to dark matter and produces the dark sector, then it would be very difficult still to.
Then it wouldn't be secluded. I think they would talk to each other. Yeah, probably, right? I mean, they would have an effective interaction.
Yeah.
By the inflaton, integrating out the inflaton makes an effective interaction, probably. Is that what you mean, or did I miss?
That's what I'm thinking. Yeah, but I mean. But in a completely secluded dark matter, like how would you then produce it in the early universe? It must couple to inflaton somehow.
Yeah, okay, it's a good question. I don't know, probably. I didn't think about this this kind of model, but how do you produce it?
Unless you produce it gravitationally, I don't know. Is that possible, then, Joe? Can you produce?
Absolutely, people have looked at this. I mean, dark matter could be you know, because indeed, exactly right. Because if it only has gravitational interactions, it will be produced in evaporation of black holes, because you know, just black holes evaporate to everything. It will evaporate to dark matter. And in fact, there was a paper by John March Russell and his students, and some other follow-ups from various people about this gravitational black hole genesis of dark matter. Indeed.
I see.
So this could be a secluded sector, example of a secluded sector.
Yeah.
Yeah.
Yeah, I didn't know this. Yeah, I'm taking a note.
Yeah, that's an interesting idea actually, and they did a decent calculation about, and there's been follow-up that does an even better approximation to this, and yeah, it's a cool idea actually. It's very cool because indeed, if it's completely secluded, that's the only way to produce it, and then the question is, do you have enough, you know, whatever primordial black hole density in order to produce enough dark matter, etc. It's a different in the details, but the idea is very nice.
I see. So it doesn't have to be a particle dark matter if it is gravitationally produced.
I think it has to be a particle in order to be produced in black hole evaporation, but yeah, I think so. I'm not sure. Yeah, I think so. It has to be.
And it doesn't have to have any interactions with the known physics, with standard model particles.
I don't think so. No.
Yeah,
I think it just the black hole evaporates to all the degrees of freedom. No, equally. I mean,
in principle, there are other ways. If you have something like a Kastner universe, it will have particle creation, and you can create any particles that interact with the gravitational field that way. But that's not a realistic cosmological model. That's the difficulty. But one can imagine scenarios where gravity would generate it.
Yeah. By realistic, you mean experimentally accessible?
Well, observational, I suppose, cosmological observation. Kastner universe is kind of chaotic. It has expansions in different directions and contractions. It's a very dynamic universe, which doesn't look like it corresponds to anything.
I see.
How then is the name of the Casimir universe?
Kastner.
Okay.
There were models that were considered in the late 60s.
Okay, interesting. I didn't know. Yeah, interesting.
I mean, when people in quantum field theory and curved spacetime considered particle creation, there are old papers of Leonard Parker who looked at particle creation in the early universe.
Okay,
just theoretically, just a theoretical concept of if you've got a dynamical gravitational field, it can generate particles.
Yeah.
So in principle, you can do it.
Yeah, but it's not really observationally viable.
Well, I'm not the right person to ask that, but I would think not, because these they have fallen out of favor with inflation and things like that. If you have an inflationary scenario, then all of that type of stuff gets washed out.
Yes.
It's very difficult to fit those with that. But I'm just talking about in principle.
Yeah.
How you can generate things from dynamic gravitational field.
Yeah.
And I think the black hole one sounds like it's very much in that same spirit.
Yeah.
But
yeah, exactly. I mean, it must. I mean, so that's interesting to know that this idea of gravitational genesis of dark matter is not new.
Yeah.
Well, it wasn't for like dark matter that they were discussing. It was just genesis of matter in general.
In general, indeed.
Yeah.
That was the original context.
Yeah, but if you produce matter, you produce everything. And
yeah, exactly.
Yeah, so this black hole is just maybe it's just a different mechanism to doing this, and maybe it's more. But indeed, it's.
Oh, that's very good.
Hopefully, it's not secluded, but.
Yeah.
Exactly.
But it's
becomes very difficult if it is.
Yeah.
Yes, I mean, we're really. Yeah. I mean, yeah, one thing that has been happening recently Well, I mean, there's been a resurgence in people thinking about axion dark matter and light dark matter, wave-like dark matter, and things like this, fuzzy dark matter. And so people are now thinking much more, expanding much more in the mass range of dark matter.
Yeah.
And yeah, because we're not seeing anything in this range. And so hopefully we see something soon. That's the hope. Whatever mass it has, or whatever search strategy it shows up, then we can start thinking about how to disentangle everything else that comes with it.
Yeah. In the beginning of your talk, you said something about there has been a slight bump that's been observed.
Yes, this excess at, yes, there's been a small excess in this xenon experiment.
I didn't hear about this.
Yeah, let's see. There were some papers trying to explain it. I don't know what the status of this is at the moment. Yeah.
So around what mass was it?
I'm trying to pull up the plot so that I don't actually probably
Google would be
yeah, Google is the best for this. There might even be a blog post by Adam Filkowski. I don't know if
probably, yeah. Oh, is it just in the electronic recoil event?
Yeah, indeed. It's only the S2 signal. It's only an electronic recoil.
I see.
And they even had a new thing. I think I don't know if this has been done before by dark matter experiment. They released their data for this so that people can. So that's kind of a cool.
Yeah, that's very cool.
Yeah. So people can think about what's causing this. Excess. So you found a plot. I was just still trying to,
well, I found a paper. It's from 2006, I think. So it's not very new, but oh no, actually, the archive number is from 2006, but apparently they've.
Oh no, this is much newer than that. I think.
From 2020.
Here, I can share this maybe. New share. So this is the blog post. So this, for the students who don't know, this is, I mean, he doesn't write a lot anymore, but this blog is
very nice. Yes.
He always gives a nice summary. So here's the energy recoil that. Oops, sorry. So it's the excess is. I mean, it's hard to even see by eye, but there's an excess here. I think that's the one that's causing the excitement, and. Indeed, it's in electron recoils, and so he says. So this is the 1 ton, xenon 1 ton.
Yeah.
Where does he say what the excess is? Yeah, okay, but there's a bunch of papers that people try to explain this with an axion or.
Yeah.
You know, things, dark photon. I think even can do this.
Probably, yeah.
Dark photon, see, it says here, and also neutrinos. People.
Oh, even scalar dark matter can do this, yeah.
Yeah. So, so yeah, it's something. It's an interesting excess, and yeah. So it's from 2020. It's not super old. Yeah. And I don't know what the recent status of this is, but anyway, it's a very good blog to keep an eye on for these sort of anomalies that are happening. Yeah, including he wrote something recent on the W mass anomaly. So.
Oh, that's good. Yeah, I'm gonna go read that one. Yeah.
It's a very nice summary of what's the story and
yeah, because with that one, I'm not sure. Yeah, I'm not 100% sure why we interpret it just as W mass. Because I mean, it contributes to the electroweak rho parameter. Why not Z mass, or why not alpha S? Why not?
Well, no, because they look at the spectrum of this MT transverse mass distribution, and this is shaped by the W. I mean, the problem, it's like looking at the Z line shape. You just cannot look at the W line shape because you don't have the neutrino. But in the Z line shape, so you can just fit, you can just extract it directly from the data, what the mass is. Because it puts where this threshold is, or this, you know, without smearing, this would be be an edge, but because there is showering and all that stuff, it's not an edge, it's a sort of a shoulder in the spectrum. I don't know if he has this plot here, but you can see it in the, no, it's not you can indeed interpret it as the mass, because it's extracted directly from I mean, there's no such thing as a mass measurement. Mass is always extracted. It's not a physical parameter in a sense, but it's directly extracted from this observation. Yeah. No, it's a very strange thing, and yeah, we'll see what happens if it's new physics or some systematic. I mean, it's an impressive measurement. If you you haven't seen it, the precision that they claim is 9 MeV on 80 GeV. So this is a 1 in 10,000. 1 part in 10,000 is the precision that they're claiming. It's very, it's the most precise measurement of this mass so far.
Of course.
Amazing. It's
I think it's disputed, as we heard from John.
I completely agree. It's very hard to believe that this is.
Certain people are not. Certain people are not so convinced.
Yeah, but on the other hand, all the criticisms have been. I mean, for example, there's this criticism about the Monte Carlo generator that they used, and
which is an old one.
But then there was a paper by the authors of this Monte Carlo generator, and they said even if they used the new one, it would only shift the mass by 10 MeV. The discrepancy at the moment is 50 MeV or something like this, maybe even more. So I don't know.
But why is this only coming out now? I mean,
because they took them a long time to analyze the data. Apparently, I'm not sure exactly why it took so long, but it's a big analysis now. I mean, it's a very and all the authors are now also working in other experiments. So I don't know.
Well,
it took them 10 years.
And also, if he isn't agreeing with other things, you need to be a little bit more careful, just to double check.
Yes.
And double check again. Just.
Yes. I don't know exactly. Indeed, exactly.
Because any bit of sloppiness will be picked up.
It's very easy. At this precision, it's unbelievable. No? Anything could shift you by a lot. And there was some blog post by an Atlas experimentalist who was talking about how hard it is to make this measurement, because it's so sensitive that apparently there were two effects typically they assume that the beams are head on, that the beams but the beams are a little bit offset for a couple of reasons. One of them was that the position of the Atlas detector with respect to the beam line already has some of this shift, and when they take this into account, shifted the mass in one direction. But then when they accounted for the fact that the detector sagged under its own weight for sitting for this, then it shifted it the other way. So it's amazing.
Yes,
it's like
a very nice contribution by a graduate student, I believe.
Yeah, I think you're right. Yeah, I think so.
Oh, wow.
Indeed. It was a graduate student who did this. Yeah, indeed. Exactly. Yeah, so you read this. Yeah, it's very interesting. I mean, you have to understand the detector super, super well. And this is incredible precision.
Their job is much harder than. The experimentalist job is much harder than our job.
I'm aware of it.
I mean, exactly. So many things that we don't even bother to. I mean, we don't even think about that you have to consider.
We have our own difficulties.
Yeah, the most that could go wrong in our code is just a factor of 2 or.
We don't even bother with the normalization most of the time, right? So
Exactly.
they have to worry about that.
The weight of the experiment shifting something.
No, I mean it's. I mean, just even luminosity, the luminosity uncertainty is PDFs. I mean, here PDFs are also one of the criticisms that they maybe underestimate the PDF uncertainty or. It's hard.
I'm going to stop the recording.
It's
just far beyond the subject matter. Okay. Thank you very much for
thank you, Fady. It was
for your time and indulging us.
Thank you for your time. Yeah, absolutely. My pleasure.
I really enjoyed it as well. Thanks for